Hey everyone, so this is the third and final video of Newton's 30 laws. This is probably one of the most basic law, but at the same time, probably the trickiest to spot. Now, I do want to point out that I use the term tricky. If you haven't been picking it up yet, I try to differentiate the term difficult with tricky. A lot of things and concepts in physics, and especially the AP, uh, falls into the tricky range. There are some things that are difficult that require a very extensive understanding and knowledge of math, of higher thought, of being able to connect so many different things together. Tricky things, though, are for the most part really basic, but easily overlooked or easily confused. So that's the idea of Newton's third law: is that it you can easily overlook when it occurs, and you can sometimes the way that it's phrased can sometimes think that you have to approach it in a different way. Now, Newton's third law is actually very similar to the first law in that you've already seen it. Now, this one, like we talked about, we already know why objects move and how they'll move. So this kind of brings into fact where these objects come from and how objects interact with each other. And that's the key thing, is that typically Newton's third law comes from the interaction of two different objects and the forces that come from that. So here's a perfect example. Consider a case where a man's on a skateboard and throws the basketball forward towards a friend. Does the man stay still or do they move? And if so, in which direction? Now, Newton's third law is for every action, there's an equal opposite reaction, meaning that when this man is on the skateboard and he throws the ball forward, he applies a force on the ball going forward. But according to Newton's third law, while the man applies a force to the ball going to the right or forward, the ball is going to apply a force on the man in the opposite direction. And not only does the ball apply a force onto the man, it applies the same force onto the man. That these two forces are going to be in equal and opposite direction. Now, keep in mind that these two forces do not occur on the same object at the same time. This is actually a big mistake that people think. They think that cases like an object experiencing force of gravity and then the normal force pushing up on it is the whole part of equal and opposite Newton's third law. That's not the case. Newton's third law is the fact that when an object is on a table, the object applies a force down on the table, and the table exerts the same force up on the object. If I push a dresser, I apply a force onto the dresser, but the dresser applies a force back onto me. That we apply these forces together, equal and opposite, on different objects. So if you were to draw an FBD of me pushing a dresser, there would be a force acting on the dresser going in one direction, and then I would have the same force. I was going to say a different force, but I would have a separate force acting on me. So this is the dresser. I'm applying a force going to the right on it. The dresser would apply the same force on me going in this direction, and these two forces would be equal and opposite. So this is an extremely important thing. It leads into a lot of other concepts, but it's important to note that anytime you have objects that are interacting, this is always happening. So if we go back to that scenario where we have an object on a table like this, if we looked at the forces acting on this block would be experiencing a force going upwards, which we normally call the normal force. But if we actually looked at the table has its own FBD, and it would also feel the same normal force pushing down on it. And these two forces are equal and opposite. So that's Newton's third law. Like I said, it's a fairly basic law, and when I bring it up, it's easy to go, okay, yeah, sure, that makes sense. But it's hard to, like I said, pinpoint when this is occurring. So I usually like calling it the law of action reaction pairs because it basically says that there's a symmetry between the interactions of two objects. That whatever one object experiences, the other object also experiences. So if you push a stroller, then the stroller technically is pushing you back. You may not think it, but that's what's actually happening. Technically, you can actually get away with the claiming self-defense by hitting someone because technically when you hit the person, that person applies the same force back onto your hand. This is actually why when you hit something, your hand ends up hurting because if you were to, let's say, punch a brick wall, you apply a force onto the brick wall, but the brick wall applies the same force back onto your hand. So both the wall and your hand are experiencing equal and opposite forces. And if you apply a hard enough force, that force is going to essentially bounce back to you and end up hurting your hand. Uh, this is pretty much the reason. Like I said, it's a very important law, and one of the reasons why it's so important is that it actually explains how things like rockets, jets, airplanes, walking, swimming, how all these things actually work. If you think about it, the way we walk is that we push backwards on the ground, and then the ground, because of Newton's third law, pushes us forward. There's an equal and opposite forces acting on us. When you go swimming, you literally are cupping your hand and you're pushing the water back. And by doing that, by pushing the water back, the water pushes you forward. So this is the whole action reaction stuff. In the case of the jets, you know, molecules and energy is being expelled out in one direction, and then that propels the object going forward. So here's an example of the rocket pushes on the gas, and then the gas pushes on the rocket. So a lot of times you just switch the two terms, and you get your Newton's third law action reaction pairs. But again, the key thing is that these two forces aren't happening on the same object. That's not how action reaction works. One object experiences one of the forces, another object experiences the other force. Uh, this can also be seen in a lot of recoil problems. So if you ever seen someone who shoots a gun or a cannon, and there's all this recoil from it, it's mainly because of the fact that the guns apply a force onto the bullets going forward. Those bullets will exert an equal force. This is supposed to be an equal line, not bigger, but it exerts an equal amount of force going backwards. So the forces are equal. Now, what's important to note is that I keep saying that the forces are equal, uh, but this is something that people tend to confuse because they end up seeing the acceleration of two objects and they forget that mass matters. So while the two objects will experience the same force, they won't experience the same acceleration, right? The bullet goes significantly faster when it leaves the gun because of the fact that it has a smaller mass. So the force on the bullet is going to be equal to its little tiny mass times by a big acceleration because it ends up going really fast. Now, this bullet force is going to be the same as the force on the gun. And if we look at the forces on the gun, it has a much bigger mass, and because of its bigger mass, it'll end up having a smaller acceleration, which is why the gun moves backwards, but doesn't move backwards at the same speed that the bullet leaves. This is also seen with car crashes. So when two cars get into an accident, they exert equal and opposite forces onto each other. The forces are the same, but because of their difference in masses, could end up resulting in different amounts of damages. For example, if you have a giant truck getting into an accident with a very tiny Mini Cooper, the Mini Cooper is going to get absolutely destroyed in the accident because the high mass of the truck gives it a lower acceleration during its collision, while the small mass of the Mini Cooper results in a very high acceleration that it experiences, resulting in it being damaged. This is also done with bugs getting hit by a bus, right? If you have a bug being hit by a bus, the forces are equal, but because their difference in masses, their accelerations are going to be different. The bus has such a high mass that it basically has almost no acceleration. It just keeps moving forward as if nothing ever happened. But the bug, because of its significantly smaller mass compared to the bus, will accelerate so much that it literally explodes from the impact. So yeah, these are just more videos of that idea. This also, I just put this in as a joke, but Newton's third law actually explains troll logic, and in particular explains why troll logic doesn't work. So you might have seen images of this at some point scanning the internet. Cases like this of, hey, if we put a magnet on an object, then we could get infinite power or infinite movability, things like that, anti gravity, having two magnets. But the problem is that this doesn't work because according to Newton's third law, yes, this magnet will attract this object going forward, and this will attract the magnet going. I keep making these different sizes, but these are supposed to be equal forces. So they'll experience equal amounts of forces going in opposite directions. But because of the fact that these two objects are being connected, like they are here, these two equal and opposite forces will end up canceling out to the point where there's nothing happening. What will end up happening is this will just move forward, this part of the car will move back, but the overall structure will not move forward. Just those two parts will move forward. Similar thing to this, this part will move down. This might move up a little bit, but probably the gravity will pull it all down, and they'll get connected, but this entire structure will not go upwards. All right. So here's the first question. Pause video, work cell phone, go for a second. All right. So like I said, you're going to notice that the answers to all these questions are really basic and easy to see. But the problem is seeing it. Right now, when you're seeing these problems, you're seeing it in the light of these are all Newton's third law questions. And we'll see some examples later on when these can be used in other non third law questions. But you'll just know like, okay, everything's always going to be the same. But keep in mind that this is a really easy question to get tripped up on. So for this one, compared to the magnitude of the force exerted on the stroller by the man, the force exerted on the man by the stroller is the same. Now, one thing to keep in mind is this idea that if you look at the phrasing of it, all they do is they take the word stroller and man and reverse it. That's it. So that's one way that you know that you're dealing with a Newton's third law question, because they'll just take the two terms and flip them and expect you to think that, oh, everything's changed now. All right, here's the next one. Pause video, work itself. I'll go in a second. All right, so we have these two carts being affected by a spring. One car experiences 1 Newton. What does the other car experience? Also 1 Newton. Again, Newton's third law says that the forces have to be equal and opposite. So one object feels one, the other one also feels one. Here's the next one. Pause video, work itself. I'll go in a second. All right, again, you'll notice is that one thing that they always do is they love to add in information about masses of objects and sometimes even different accelerations. And a key thing to keep in mind is that none of that matters. They're all red herrings in these types of problems. The force on the Earth on the moon is F, so the moon on the Earth must also be F. They exert equal and opposite forces. Okay, here's the next one. Pause the video, work itself. I'm going for a second. Now, here is pretty much the next step to a lot of these Newton third law questions, where um, the whole question doesn't stem from that the forces are the same. Here they tell us that we have a cannon firing a cannonball. We know that the cannonball experiences 100 newtons of force, but the cannon, they want to know what the acceleration is. Now, this actually ends up becoming essentially a scenario one, scenario two question, right? So if we look at it, we have all this information. We have the mass of the cannon is 100. We know that the mass of the ball is 20. Forgive the fact that I'm not putting the units. We know the ball feels a force of 100. And we're looking for the acceleration from the cannon. And you might be thinking, we don't have enough information. If I just use the cannon information, it's not enough. I can use the ball's information to figure out what the acceleration is here, but that doesn't really help me. The key thing to realize is that by them telling me the force acting on the ball, I automatically know the cannon's force, because these two forces have to be equal and opposite. So if the ball experiences 100 newtons, then the cannon experiences 100 newtons. And now I have enough information to do F net equals ma. So again, the key thing is just to recognize that we have this information, that Newton's third law is telling me that these two forces are equal and opposite, right? And that's it. Like I said, we'll see more examples of Newton's third law in some of the more complex problems. Uh, but the key thing is to try to be able to recognize when it appears. Like I said, this can be difficult, so I'm going to try to include as many questions as I can every now and then in order to kind of show you different examples of when Newton's third law pops up. All right. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.